Hello! In this video, we are going to prove the following theorem. Suppose G is a group with identity element E, and suppose A and B are elements of G with finite order. If the greatest common divisor of the order of A and B is equal to 1, then the intersection of the group generated by A and the group generated by B consists only of the identity element. Now, in proving this theorem, we are going to be using Bézou's lemma, which tells us about the greatest common divisor of two integers being equal to 1. Suppose A and B are integers that are not both 0. Then the greatest common divisor of A and B is equal to 1 if and only if there exist integers s and t such that as plus bt is equal to 1. Okay, so now let's get into proving this theorem. Now to start with the proof, let's suppose that the greatest common divisor of the orders of A and B is equal to 1. From here, we want to show that the intersection of the group generated by A and the group generated by B consists only of the identity element. Now, for convenience, we're going to say that the order of A is equal to P and the order of B is equal to Q. And so in that case, this is the greatest common divisor of P and Q. And then, by Bézou's lemma, there exist integers s and t such that ps plus qt is equal to 1. Now, the whole goal is to show that the intersection of the group generated by A and the group generated by B consists only of the identity element. And the way we're going to do that is we're going to show that the identity element belongs to the intersection of the group generated by A and the group generated by B. And then we're going to show if we consider an arbitrary element of the group generated by A intersect the group generated by B, then that element must be the identity. In other words, we're going to show that these two inclusions are true. So let's start by showing the first inclusion is true. So we're trying to show that the identity element belongs to the intersection of the group generated by A and the group generated by B. And to see how that happens, I'll notice the identity element is equal to A to the power of 0. So this is A to the power of some integer, so it must be an element of the group generated by A. So this shows that the identity is an element of the group generated by A. And similarly, the identity element is equal to B to the power of 0. But this is just B to the power of some integer, so it must be an element of the group generated by B. So this shows that the identity belongs to both the group generated by A and the group generated by B, so it must belong to their intersection. And this shows that the first inclusion is true. And another way that you could argue this is by saying the group generated by A and the group generated by B are both subgroups of G. And in fact, the intersection of two subgroups is also a subgroup, so the intersection of the group generated by A and the group generated by B is also a subgroup of G. And every subgroup contains the identity element, and that's the reason why this inclusion would be true. Okay, but in any case, we verified that this first inclusion is true. Now let's verify the second inclusion. To do that, let's give ourselves an arbitrary element of the intersection of the group generated by A and the group generated by B. I'll call that element C. From here, we want to show that C is the identity element. Now, we know that C is an element of the group generated by A, so this means C must be equal to A to the power of some integer. I'll call that integer I. And also, C is an element of the group generated by B, so C must be equal to B to the power of some integer. I'll call that integer J. And now, to see how C is equal to the identity element, we'll notice we know that C is equal to C to the power of 1, and 1 is equal to PS plus QT. And then by properties of exponents, this is just C to the power of PS times C to the power of QT, and it'll be nice if we replace the first C with A to the power of I, and we replace the second C with B to the power of J. And then by properties of exponents again, we can just multiply the exponents. So we have a to the power of IPS, and here we have b to the power of JQT. But then by properties of exponents again, a to the power of IPS can be written as a to the power of p to the power of SI, and b to the power of JQT can be written as b to the power of q to the power of TJ. But since the order of a is equal to p, that tells us that a to the power of p is equal to the identity. Since the order of b is equal to q, we have b to the power of q is equal to the identity. So this is just the identity to the power of SI times the identity to the power of TJ. Now the identity to the power of any integer is equal to the identity. So this is just the identity times the identity. And by definition of the identity times the identity is equal to the identity. So this chain of equalities shows that C is equal to the identity element. So we have shown, given an arbitrary element of the intersection of the group generated by A and the group generated by B, well then it must be equal to the identity element. So that verifies that this second inclusion is true. And these two inclusions tell us that they must be equal. And so this completes the proof. And so yeah, that's pretty much it for this video.